So now that we've learned about ionic and covalent bonding, let's talk about some unusual bonding patterns that we see. And we're going to talk about 3 unusual bonding cases here. So we're going to talk about bonding with hydrogen, we're going to talk about something that's called expanded octets, and then finally we're going to look at something called polyatomic ionic bonding. So these first 2 that we're going to talk about deal with covalent bonding, and the last one is focusing on mostly ionic bonding. We'll talk about that when we get there. So let's start with bonding with hydrogen. Now, hydrogen's not all that weird when it comes to bonding, but it has one main exception, and that's the fact that hydrogen does not follow the octet rule. And the main difference with this is hydrogen just isn't big enough to accommodate 8 electrons. So it doesn't want 8. In fact, hydrogen only wants 2 electrons when it bonds. So it's going to make one single bond, and it's going to have no lone pairs. So let's look at some examples for this. So our first example is carbon with 4 hydrogens. So we have our carbon that's going to go in the middle, and we know that carbon has 4 valence electrons. Our hydrogens are going to orient themselves around, and each hydrogen has 1 valence electron. Now remember, it takes 2 electrons to make a bond, and so conveniently enough, we can see that we have pairs of electrons formed. So I'm going to erase the dots and replace them with single lines. So now we still have all of the electrons. Each hydrogen brought 4, each hydrogen brought 1 for a total of 4. Carbon brought 4, so we had 8 total. We still have 2, 4, 6, 8 valence electrons. They're just all in bonds. And our carbon has the 8 that it needs to follow the octet rule, 2, 4, 6, 8. And hydrogen has its 2 that it needs. So 2, and then this one has 2, and then 2, and then 2. Let's look at our next example, H2O, or water. So this is also one of the exceptions to the first element in the formula is going to be in the center, because this doesn't work if we put hydrogen in the center. If hydrogen is only going to bond once, we can't have a hydrogen in the middle to bond to another hydrogen and an oxygen. So we're going to put oxygen in the middle. And oxygen, we know, has 6 valence electrons. So 1, 2, 3, 4, 5, 6. Then we're going to put a hydrogen here with its 1 valence electron, and a hydrogen here with its 1 valence electron. And then they're going to pair up. So these guys are going to pair, and these guys are going to pair. So I'm going to erase my dots, replace them with lines. And so that's the covalent Lewis structure for water. So each hydrogen has its 2 that it needs. Oxygen has 8, 2, 4, 6, 8, and all of the electrons are still there because I started with 6 from oxygen, 1 from each of the hydrogens, so 8 total, and I still have 2, 4, 6, 8 here at the end. Okay, let's look at one more example. So CH2F2. So carbon's going to go in the middle, and carbon has 4 valence electrons, and then it's going to have 2 hydrogens, each with 1 valence electron, and then 2 fluorines, and we know that fluorine has 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Again, my dots are going to pair up, so any unpaired are going to find another unpaired to form a pair. So these 2 are going to pair up, so I'm going to erase those and draw a bond. These 2 are going to pair up, so I'll draw a bond there. Same with these guys, and then same with these guys. So my hydrogens don't have any lone pairs, they're just going to form their single bonds, and my fluorines will have their lone pairs because they follow the octet rule. Carbon has its 8 because it follows the octet rule, and we still have all of our valence electrons we started with. So hydrogen is just one slight example, or one slight exception to the octet rule. So let's talk about our next unusual bonding situation, and that's something called an expanded octet, and it's exactly what it sounds like. This means that the central atom can expand beyond the octet rule. It can have more than just 8 valence electrons. And we usually see this with elements such as phosphorus, sulfur, and xenon are the most common ones that we see. So phosphorus and sulfur we know are nonmetals. Xenon is a noble gas. This is one of the few exceptions to noble gases don't bond. Xenon will bond every once in a while under very specific sets of conditions. So let's see what this looks like. So if we have PCl5, our phosphorus is going to go in the middle. Let me grab my periodic table. So if we look on our periodic table, we see that phosphorus has 5 valence electrons. I'm going to go ahead and draw those in. 1, 2, 3, 4, 5. But we have 5 chlorines. Now that doesn't make sense. If phosphorus is going to bond to 5 chlorines, that means it's going to have 10 electrons minimum just in those 5 bonds, which tells us that this is going to be an expanded octet. This can happen. If we have a formula for it, we know that this can physically form, at least in our situations, and so we know that this is going to be an expanded octet. So that means each of these electrons, even these guys in the pair, are going to form a bond to a chlorine. So let's draw our chlorines in. And each chlorine has 7 valence electrons. So in this case, in order to form the 5 bonds that are necessary, each of the valence electrons for phosphorus are going to have to bond with the lone electron on chlorine. So there's 1, 2, 3, 4, 5. So it still follows our other rules. We didn't gain or lose any electrons. However, in this situation, instead of having 8 electrons only around the phosphorus, we have 10 because this is an expanded octet. So let's look at SF6. This is going to look very similar. So the fact that we have 6 things bonded to sulfur means that at minimum, we're going to have 12 valence electrons around sulfur. So that tells us that this is going to be an expanded octet, and that's okay. So we're going to put our sulfur in the middle. Sulfur has 6 valence electrons. So that tells us that each of these valence electrons is going to form a bond to a fluorine. So we're not going to have any lone pairs. So even the electrons that are in the pairs are going to form individual bonds to our fluorines. And so we have 6 fluorines. So 1, 2, 3, 4, 5, 6. And each fluorine has 7 valence electrons. And so each of the single electrons on fluorine is going to bond with an electron from sulfur, even the ones in the pairs. So there's 1, 2, 3, 4, 5, 6. So again, we're still following our rule that we didn't gain or lose any electrons. However, sulfur now has 12 electrons around it instead of just its standard 8. So that makes this an expanded octet. And then finally, let's look at XeF4, so xenon and fluorine. So this looks like it might still be okay because it just has 4 things bonded, but xenon's a noble gas. Xenon already has 8 valence electrons. So let's look at what this might look like. So xenon's going to go in the middle, and it's going to have 8 valence electrons. So let's go ahead and draw those in. And then it's going to bond with 4 fluorines. And each fluorine has 7 valence electrons. So each single electron is going to find an electron from xenon. Now, they're all in pairs, so we're going to start by splitting up one pair at a time. So let's split up this bottom pair, and one of those is going to bond with this fluorine, and one is going to bond with this fluorine. And then we can do the same with this top pair. So let's split up that pair, and one electron from that pair will bond with that fluorine, and one will bond with this one. So in this case, they didn't all bond. We have 2, 4, 6, 8 electrons in bonds, and we have 2 lone pairs. So xenon forms an expanded octet, and it can bond with the 4 fluorines. So that's what an expanded octet would look like. Let's look at our last example of unusual bonding, which is polyatomic ionic bonding. Now, it's ionic bonding, so we're still going to see the positive and the negative that are going to attract each other to form that bond through electrostatic attraction. However, it's polyatomic because it's going to have both ionic and covalent bonds in it. So polyatomic ionic bonding happens when compounds have both ionic and covalent bonds. And we can see this in our 3 examples. So our first example is NaOH. So it has a metal. That means it has to be an ionic bond. However, it has 2 nonmetals. So that tells us that this right here, this OH, is going to be a polyatomic ion. So there are covalent bonds within that ion. Same with magnesium carbonate. Magnesium's a metal, so it has to be ionic. So magnesium's going to be the positive part. The CO3 is going to be the negative part. Within this CO3, we're going to see covalent bonds. And then finally, KNO3, potassium is our metal, so it's going to have a positive charge. Our NO3 is going to have a negative charge, but since there's more than one atom there, it's a polyatomic ion. And so we know that there are going to be covalent bonds. To help you with this, on the back of your periodic table, there is this big list of polyatomic ions and their charges. So if you're ever not sure, if you see more than one nonmetal, you can always flip your periodic table over, look and see, does it match one of the polyatomic ions on the back? If it does, you know that this is what it's going to look like when it goes to do its bonding. So let's start with NaOH as our first example. So we know that sodium has 1 valence electron. So we'll go ahead and draw that in. OH, we know is going to have a covalent bond. So let's think about that separately. Let's think about what that would look like. So we have an oxygen that has 6 valence electrons, and we have a hydrogen that has 1. So those 2 unpaired electrons are going to form a bond, but we have an issue. So hydrogen's happy with just 2, so it has its 2. Oxygen, however, has 2, 4, 6, 7. It only has 7 electrons. It needs 1 more. Where do you think that it's going to get that 1 electron? Well, it's going to get that 1 electron from sodium, because sodium wants to give it up. So sodium's going to give its 1 electron to the OH. So here's what happens. So we have a sodium that forms a positive 1 charge. We have our OH that now that it's taken that electron from sodium, it now meets its octet rule, but that has a -1 charge because it's now gained an electron. So now that they're positive and negatively charged, now they attract each other and form that ionic bond. Let's look at a little bit more complicated example. Let's look at magnesium carbonate. So magnesium has 2 valence electrons. And carbonate, let's look at that separately because we know it's going to have covalent bonding. So we're going to have carbon with 4 valence electrons and 3 oxygens. And each oxygen is going to have 6 valence electrons. Okay, we're going to start by at least making 1 bond from a carbon to an oxygen. So we're going to take these pairs that are right here and form those into a bond. Now, my carbon still isn't happy, it needs another electron, and none of my oxygens are happy. They still need more electrons. So we're going to go ahead and make a double bond between our carbon and this oxygen over here. So that'll take care of those 2 electrons. They're going to share and form a bond. So now this oxygen has 2, 4, 6, 8. My carbon now has 2, 4, 6, 8, so we're good so far. This bottom oxygen has 2, 4, 6, 7. We have a little bit of an issue. And this left oxygen has 2, 4, 6, 7. Again, another issue. So we need a total of 2 more electrons. Where are those electrons going to come from? Well, they're going to come from magnesium, because magnesium wants to give up 2 of its electrons. So this electron is going to go to that oxygen, and this electron is going to go to that oxygen. So we're going to end up with magnesium with a +2 charge, and we're going to end up with our carbonate now everyone has all 8 valence electrons, but since it's gained 2 valence electrons, it has a -2 charge.